Okay, so the next part of this lecture and the next one will be taken up by discussing the four forces that the respiratory muscles have to work against in order to inflate the lung. Okay, and the first one is, well, we'll go over these, each one in detail. Elastic recoil of the lung, recoil of the chest wall, surface tension, and airway resistance. So let's look at elastic recoil of the lung. Okay, so we can think about the elastic recoil of the lung by creating a static compliance curve or a pressure volume curve. Okay, so on the x-axis we have pressure. Okay, so we apply a certain pressure to the lung, okay, and we measure the volume, okay? And it's a static compliance curve, so if we change the pressure, we wait until the lung comes to steady state, and then we make the measurement. If it weren't static compliance, it would be dynamic compliance, and that's you measure things during movement, and it's more complicated. Okay, so static compliance curve, we're just measuring the elastic properties of the lung. Okay, so we increase the pressure, and the volume increases. Okay, and here we have a higher volume, we increase the pressure, and we increase the volume. Okay. Now the slope of the pressure volume curve is called the compliance. Compliance is how easy it is to inflate the lung. Okay, that means pretty much the same thing as compliance in individuals. If someone is compliant, you ask them to do something and they do it without resisting at all. Okay, so they're very compliant. So if you're trying to inflate the lung, you add some pressure, and at the low part of the curve, the compliance is high, the curve is steep. A small increase in pressure results in a large increase in volume. Okay, the curve gets flatter as we go towards higher volumes. Okay, the same increase in pressure produces a smaller increase in volume. The compliance is less. Okay, so this is our pressure volume curve, our compliance curve, static compliance curve for a normal human being. And what we'll do quite a bit of is talk about the normal situation, and then we talk about what happens if things are not normal. And so it turns out that lung compliance there are problems if it's too high or if it's too low. Okay, so this curve is a little bit complicated. It's not a straight line. It's steeper at the bottom. And if you think about the cross-section of lung tissue, okay, there's small bits of tissue and mostly air. It's a very spongy tissue, so you can imagine it would be pretty easy to inflate it a little bit. Okay. But once you inflate it beyond a certain point, you're starting to stretch the walls sideways, and so the compliance decreases. So at the bottom part of the curve, it's like blowing up an air mattress. Things just kind of unfold, but then towards the top, you're actually stretching the tissues, and so the compliance becomes lower. Okay, well, that's normal compliance. In pulmonary fibrosis, compliance is too low. Okay, and fibrosis is an example of a restrictive disease. There are obstructive diseases where airflow is obstructed, and there are restrictive diseases which mean that it's hard to inflate the lungs. Okay, so in pulmonary fibrosis, there's extraneous fibrous tissue growing within the lung parenchyma, and so instead of just having these delicate little alveolar walls, you have now a lot of excess tissue, and it's going to be harder to stretch the lung, harder to inflate it. Okay, so with the same effort, a person with fibrosis will not be able to inflate their lungs as much as a normal person. Okay, so it's pretty clear that why low compliance would be a problem. What might be less obvious is why high compliance would be a problem. But it turns out that it is, and we'll spend a fair amount of time today trying to explain why too high compliance creates a problem. Okay, so with obstructive diseases, you can get abnormally high compliance, and it's easy to inflate the lungs, but it turns out that this creates problems. Okay, so if we look at cross sections of lung parenchyma, here's the normal tissue. Okay, and we have lots of little air spaces and little alveoli. Okay, in emphysema, there's destruction of lung parenchyma. Okay, so you can see there are just large areas that are just empty space. Okay, instead of having lots of little alveoli for gas exchange to take place, you just have empty spaces. Okay, so that's not good. And you can also imagine that although it would be fairly easy to stretch a normal lung, if you lose lung tissue, you have less tissue there, it's even easier to inflate it. So the compliance is going to be very high. Okay, with fibrosis, we have all this fibrotic tissue growing within the lung parenchyma. And so this takes up space, which is not a good thing, but it also makes it harder to inflate the lung. Okay, it reduces the compliance. Okay. This is a somewhat complicated figure. So this shows pressure volume curves for the lung over here and the chest wall over here. So we've been talking about the lung. The chest wall has, its own elastic properties, and its pressure volume curve looks like this. It just gets steeper and steeper. The lung curve is steep at the beginning, and then it gets flatter as you go up. Okay, so if we think first about the lung, okay, now on the axis over here, we have the vital capacity go from 0 to 100%. On this side, we have total lung capacity going from 0 to 100%. And the vital capacity stops when we get down to the residual volume. Okay, so you totally breathe all the air you can out of your lungs, and you still have this residual volume of air left. Okay. Now, we saw that the lung would actually rather be at a minimal volume, okay, and this is smaller than the residual volume. Okay, and so this means that over the entire attainable range of volumes of the lung, the elastic recoil is always going to be pulling away from the chest wall, because the lungs would really rather be down at the minimal volume, but the closest they can come is residual volume, and as you increase the volume, it takes more and more pressure to inflate the lung. Okay, so the elastic recoil gets stronger and stronger. Okay, now the chest wall has its own elastic properties, and left to its own devices, it would be perfectly happy at about 80% of vital capacity. And so if you inflate your lungs completely up to total lung capacity, the chest wall will be pulling inward a little bit, the lungs will be pulling inward a lot, okay, and so it's going to take a lot of muscular effort to maintain this high volume. Okay. So the lung and chest wall together, if we add those together, we get the solid curve in the center. Okay, and this is the curve of the system as it normally is inside an intact living human being. Okay, so the curve is steep in the middle, and it gets flatter at the bottom end and at the top end. Okay, so the compliance is highest in the middle. Okay, and compliance is how easy it is to inflate, so the amount of work that you have to do to inflate your lungs is minimized where the compliance is the highest. Okay, so where do we normally breathe? Well, we relax our muscles, we go to FRC, which is shown here, and at FRC, the elastic recoil of the lungs is pulling inward, the elastic recoil of the chest wall is pulling outward, and they're pulling in by an exactly equal amount in opposite directions. Okay, that means the pleural pressure will be negative, okay, but the whole system is at rest. Okay, so now you breathe in one tidal volume and you breathe it out again, in, out. So that's your normal tidal breathing. And you're breathing at the most efficient part of the curve where the curve is steep. And in many situations, we'll see that without thinking about it, you just normally breathe in a way that minimizes the amount of work.